see what's going on. Yep. Let's start out with, are there any questions from chapter 8?
Do you know number 49? I like that did not make any sense to me
Wait, which problem from 28
at all. 49?
or chapter 8? 49. Okay.
It's the artist will rotate 3 times the rotor.
Rotates once each second while sailing through the air, contracts to reduce her rotational inertia to 1/3 of what it was. How many rotations per second will result now? The conservation of angular momentum is the key there. So this is chapter 8, problem 49. So the shorthand notation is this is what we're dealing with. L just means angular momentum. And the formula for angular momentum is the moment of inertia times the angular velocity. Now, the nice units for angular velocity are radians per second. But it could be any sort of angle or something denoting circular motion per any unit time. So what they give us here is, so it goes around once each second. So the angular velocity initially, I'll just do angular speed. Angular speed would be 1 revolution per second. And so whatever the moment of inertia is, they don't tell us what the moment of inertia of the person is. They do tell us that when the person balls up, the moment of inertia is 1/3 of what it used to be. So we can just make up a number just so that what happens afterwards is 1/3 of what we started with. So if I make this 3 moment of inertia units times 1 revolution per second. Whatever that is, that has to multiply to get the exact same thing we started. Whatever that product is, we have to have the same product afterwards. Well, afterwards, the moment of inertia is 1/3 of what it started with. In other words, 1, because I said it was 3 here, times, that's our unknown, I guess, officially, omega final. And doing the fancy math, you end up with 3 revolutions a second. So the moment of inertia was cut down by 1/3, so the spin 3 times faster.
Okay.
You want more than that?
No, that's good.
Okay.
Yeah.
Other questions from chapter 8?
Can you do 46?
Rock in the meter stick. Balance at the 25 centimeter mark as shown in the sketch. The meter stick has a mass of 1 kilogram. What must the mass of the rock be? So it's a meter stick. I know that this is 25 centimeters here. And the length of the whole thing is 100 centimeters. If you like decimals, you can do 0.25 and 1. That's perfectly fine. And I have a rock here. So the meter stick obviously has mass all along there, but one of the nice things about a center of mass is that probably in almost all the cases that you will ever deal with, you can treat it like all the weight is concentrated at the center of mass. So it's a meter stick. Where's the center of mass?
Center of the meter stick?
Say it again?
Center of the meter stick?
I would hope so. So we have weight acting there. So that's 50 centimeters. Let's make sure I didn't misread something. Rock and meter stick balance, 25 centimeter mark as shown. So the rock's at the very left end. Meter stick has a mass of 1 kilogram. Okay. So the mass of the meter stick here is 1 kilogram. What is the weight?
Nothing.
Units?
Meters per second squared. Wait, what was it that you asked? Oh,
Yeah, newtons.
yeah, sorry, I was just using the graph, the one, like the normal one.
Good.
Sorry.
So because this is balanced, we're dealing with basically the torque's balance, just like if something is in equilibrium up until chapter 8, all the forces balanced, forces up equal forces down. Here, torque's balanced, clockwise torques equal to counterclockwise torques, or torques coming out of the board equal to torques going into the board, however you want to look at it. We have a natural pivot point right here. And so the torque from this force must equal the torque from this force. Well, torque, R cross F. In other words, because this force is perpendicular to my moment arm there, it's just however long the moment arm is times the force. So the torque from the weight is, let's set up a coordinate system. Make those my positive directions. So the torque from my weight is 25 centimeters. It's positive because it's going that way, times negative 9.8. The torque from my rock negative 25 centimeters, because my moment arm is from the pivot point to where the force is applied, so it's going that way, times the weight of the rock. And the total is 0. So that is 0.245. So 0.245 minus 25 weight of rock is equal to 0, or 0.245 equals.
Are you timesing the 25 and the 9.8?
I'm multiplying there.
And above it?
Yeah, multiply there.
Oh, did you just convert it? Is that why it's 0.245?
Yeah, I think that times that, oh, that's negative.
Yeah. No, it's two.
I just got 2.5. I mean, yeah, I just got 245.
240, oh, oops, 245. Thank you. So negative 245 is equal to 25 times the weight of the rock. And so weight of the rock ends up being negative 9.8. Negative because it's downwards. And they ask for the weight of the mass.
The mass.
Mass. That's equal to mg. The minus there is just telling me it's downwards, so I don't need a minus sign here. We aren't going to end up with negative mass. And so the mass ends up being 1 kilogram. That's the formal way of doing it, just in case the numbers were different. It was convenient that they put the fulcrum right smack dab halfway in between the rock and the center of mass of the meter stick. So that was problem 46, I believe. Other questions from about this or chapter 8? Right, questions from chapter 8 or 9?
On number 43, like, I know how to do it, but I got confused because your work in the problem, like, it gave the radius, but then you used a different one. I don't understand, cause you used 10 to the third power for the denominator, but it gave us the radius. I'm just confused in how you got that
Alright,
on the answer sheet.
This is 43 on chapter 8.
chapter 9. So the big problem was the radius fit,
Yeah,
Alright.
yeah.
the planet. This distance right here was the 6.38 times 10 to the, let's see, the way they worded it, they gave it this 10 to the 6th meters. They're asking you to find G 200 kilometers above the surface of the Earth. So they're asking you to find G at this point right here where this is 200 kilometers. When you plug into our formula that G is equal to big G times the mass of Earth over the center to center distance. That's what R is, center to center distance. They want to know that distance right there. So that's part of the same orbit right there. That's R. So it's going to be the radius of the Earth plus the altitude. Now, a couple places where people make mistakes. One place is they forget about the radius of the Earth and just do 200 kilometers. Another thing is the fact that that's in kilometers and that's in meters. So we do need to get them in terms of the same unit if we're going to add them together. Since R is the radius of the Earth plus the altitude there, we have to add them. So 6.38 times 10 to the 6th meters plus 200 kilometers.
Is that what you got? Is that how you got it? I imagine.
Sorry, you missed the last thing?
I said, is that how you got it, I imagine, the 10 to the, I don't know.
Yeah, that is the, once we convert it, so kilo means 1,000. So this is 200,000 meters. And you should end up with 6.58, I think. That's 10 to the 6th, or 6580000.
And then after that, what do we do?
Then it's a plug and chug, once you recognize that's the formula you're working with there.
Okay.
So that would be 6.67 times 10 to the negative 11th times mass of the Earth.
5.98.
It's 6,
They use 6 in the,
on your answers, sheet, you use 6 times 10 to the
Yeah.
34.
6 times, yeah.
5.98 is what I've been using in class. I think that's what's in the back of the book. In this particular problem, he said 6.
6.38.
For the mass of the Earth, 6.
So,
6.0 times 10 to the 24th. Divided by this number down here, this 6580000 squared. And you come out with 9.1 or something? I'm trying to remember what the.
mine was 9.24.
Okay.
Because I used your answer sheet as a guide, and in there, you did in brackets and then parentheses, 6,380 plus 200, and then you did times 10 to the third power and all squared.
Oh, okay. The times 10 to the third power, I don't know why it was done that way, but
I mean, if it's not relevant, it's fine. I understand it the way that you're doing it now,
Okay.
so you don't have to like do it. I just wanted to make sure that it wasn't something I missed.
no, it's just, we have to get common units, and so I thought meters is more convenient because that's sort of the international standard is to do things in terms of meters, so I put that into meters. If you put this into kilometers, then you get the 6.38 times 10 to the third kilometers plus 200 kilometers. And then, when you go to actually solve it, you have to convert that kilometers to meters. So that was an extra step that I don't think was necessary. And let me distance myself from that. Those were the publisher textbook solutions.
And for a problem like this, are you just ignoring the mass of the object versus a problem like the gravitational pull between the moon and the Earth?
If I take two objects and I drop them, what is the acceleration due to gravity?
The same?
Yes. I didn't take mass into account there either. Because ultimately, I know that the force of gravity, I have two formulas for force due to gravity. I have mg, which is really convenient if I know the value of little g here. Also, I have the more formal equation, big G, mass of the object, this is of object, mass of object, mass of, I'll just say planet, over the center to center distance squared. I have mass of object on both sides, so there are factors on both sides, I should say, so I can cancel them out, and so the mass of the object does not affect the acceleration due to gravity.
Oh, okay, I see. That makes sense.
And that's how you get to this equation. All right, other questions from chapters 8 or 9?
As I brought it up earlier, 33.
33? Calculate the force of the Earth's gravity on a 1 kilogram mass at the Earth's surface. Now, they want you to use the more generalized formula, the big G M1 M2 over what he writes, D squared. But we have another way of finding it, also the mg, but let's do it the way that's the question's intended, mass 1, mass 2 over r squared. And so he's rounded off a couple numbers there. So we have 6.67 times 10 to the negative 11th. That's big G. Mass of the object, 1 kilogram. Mass of the Earth, 6 times 10 to the 24th. Over, if it's at the surface, it's basically the radius of the Earth. Now you might consider, well, don't we have to take the size of the object into account because it's center to center? A 1 kilogram mass is really not going to take up a lot of space, especially compared to the size of the Earth. And so 6.4 times 10 to the 6th squared. I guess as the 1 kilogram object started reaching out, 100 meters into space, yeah, then the size of that object, 100 kilometers into space, then the size of the object might make a difference. So that's the setup right there. So the rest is a calculator exercise. And now I have noticed that several people have having issues with the calculator, and I'm glad to see some people getting it straightened out. If, for example, if I'm typing this into one of your calculators, I'm either going to type 6.67 times, or whatever symbol your calculator uses, times 10 raised to the negative 11, or 6.67 EE negative 11.
Now, do I do that for each and every time I put that in?
Yeah, so the times 10 to the 24th, the simplest way is would be 6 EE 24.
Okay. So you guys were doing some work the other day. And, you guys was having a problem with getting the right number, and I wasn't getting you guys numbers. I got like you guys got, 1019.17, but that's not what I got. I got like 1.0387. And I was doing like I kept putting it in the same way using the E. Like I did 6.67, I did a double E, and then I did a -11, then I did times,
Okay.
and then 5.98, the double E, and then 24. And then I divided that and did 3.84, the double E, 8, and then I squared that, and I got, 101.03.
So you got 101.03
No,
at,
1.0387.
For that one?
No.
with no times 10 to the anywhere?
Right, and so I was wondering, like, well, how, I think it was, something was saying like a 19 one time, but I'm like, I don't understand. And I put that in, this is what y'all was doing in class.
Oh, for this problem you were getting,
Yeah.
you're not.
Sorry, I wasn't talking about that, but I was just saying, like, cause I'm putting it in, I think I'm having a hard time, cause you brought up calculators and
Yeah.
the problem with that, so.
Yeah, I'd have to see what you're typing in as you do it.
All right, then, so what we about to get for this one right here then, because I got 9.770, you see, I think, cause I'm not sure if I'm putting it in.
I would expect it to be somewhere around 9.8. I don't know what the book solution was.
Yeah.
Yeah, it was 9.8.
Or I also got 9.77.
Okay,
That's what I got.
so you got it.
Okay, then, so, well, we'll talk about this one right here, cause this one was puzzling, cause it was like a little bit longer, and I was kinda interested in it. And I just felt like I got the wrong number, cause everybody else was saying 1.1026. But,
Oh, you were off by,
right,
no, that's what you got, right?
yeah,
And what
that's
do we
what I
have in
got,
class?
and this is the class guy.